Hey everybody, welcome to Unit 7, Trigonometry. So we are learning trig here in geometry because what trigonometry is the relationship between sides and angles in a right triangle. So remember, a right triangle has three sides, A, B, and C, where C is opposite or right angle, the hypotenuse, okay? And remember, the hypotenuse is always our longest side. And we know by our Pythagorean theorem that a squared plus b squared has to equal c squared. That makes this triangle a right triangle. What we're going to look at today is some radical review and that Pythagorean theorem with our right triangles. So typically we're given two of the sides. So let's say that this side was 6 and this side is 8. We could find the third side by substituting in 6 squared plus 8 squared equals 10 squared. And we could find the third side to be 10. What we're going to extend this idea into with trigonometry is we're going to be able to find the measure of this angle at A. So if we needed to find this angle and we were given these side lengths, trigonometry helps us find that angle measure based on the side measures. Okay? So there's a relationship between sides and angles in these right triangles. So starting with exercises 1 and 2, the question reads, do the following lengths form a right triangle? So if we tested a squared plus b squared in, does it equal out to c squared? So looking at these three measures, 6, 8, and 9, is 6 squared plus 8 squared equal to 9 squared? Well, 36 and 64 gives us 100. Is that equivalent to 81, which is 9 squared? No. So this triangle we can't assume is a right angle. This angle here, we would find some other way. That's actually going to be a later topic as well. We would be able to find that angle measure. Now, it might be obtuse. It might be 91 degrees. It might be 89 degrees. Okay, we don't know, but it's definitely not going to be 90 to make this a right triangle with a 90-degree angle. Looking at exercise 2, one other thing. In order to put into the C, I know the 9 has to go there because, again, that's the largest number out of 6, 8, and 9. So we had to put that 9 in on the right-hand side. So looking over here, if I kind of put in the A and the B, is 5 squared plus 12 squared equal to 13 squared? So again, we're kind of asking ourselves a question here at the beginning. So 5 squared is 25. 12 squared is 144. Again, that's me knowing my perfect squares. 25 plus 144 gives me 169. Is that equal to 13 squared? 169, yes. So that will tell me that this triangle here will have a right angle between those two sides so that this 13 is our hypotenuse. And we've done the Pythagorean theorem a few different times over. Again, I kind of given you a clue over the last few days that we're going to be looking at radicals in this unit. So reducing radicals, refresher. Remember these perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, and so on. Okay? These are our number squared. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. Such that if I took the square root of 49, remember we get plus or minus 7. So what we're doing for these radicals, please express each radical as a simplified radical. Please express each as a simplified radical, if I can read today. So what we're going to do is the product of two radicals, we're essentially factoring. I remember factoring. We break something down into its smaller pieces. So we're trying to make this number under the radical a little bit smaller. So square root of 20, we're going to break down into two numbers. Now, if you need help with your factor pairs, okay, we can go in and put in 20 divided by x into the calculator, go into your table, and see what set of factors multiplies to 20. Now we're not looking for negatives. We're going to stick into the positives for right now. But our factor pairs are 1 and 20, 2 and 10, 4 and 5. Okay, 5 and 4 is just those numbers reversed. But we're going to pull out the 4 and the 5 because the 4 is a perfect square. So as you're looking at your pairs of numbers, 1 and 20, 2 and 10, 4 and 5, we pick out we pick out the pair that has a perfect square, that 4. So we break that down to square root of 4, square root of 5, and the square root of 4 is 2. 2 times radical 5. So again, we started with a 20 under the radical. Now we have a 5 under the radical. So that is square root of 20 simplified. If we had defined it to a decimal place, again, this is irrational. The decimal continues without any pattern. Okay? But 2 square root of 5 gives you the exact equivalent decimal. So these two things are equivalent to each other. One is just in a simplified format. The reason we have to simplify them is because in a minute we're going to add things together. Okay? And you can't add unlike radicals. You have to add like terms. So square root of 48 is next. We want to break that into 2 radicals. Now some of you are going to say, oh, 4 goes into that. But if I put, and I'm going to do this in pencil on purpose, if I put 4 here and 12 here, we would go and break 12 down again. Okay? And you're just going to be factoring all day. What you always want to do is this first term should always be the largest perfect square. Okay, so you want that to be the largest perfect square. So if you need help with the factor pairs, again, 48 divided by x. Go into your table. You need to pause a second. I would go down the y column here. Okay, so again, this is giving you the numbers divided by x. So when you're putting this in, we're taking 48 and dividing by every x value. So your x table never changes, your x column. So 48 divided by 1 is 48. 48 divided by 2 is 24. 48 divided by 3 is 16. 48 divided by 4 is 12. So those are your factor pairs. I go down the larger numbers and stop when I got to a perfect square. So 16 goes in 3 times. So remember, if 4 goes in, 4 times 4 is 16. So you always want to check 16 as well. So I'm going to break this down to 16 and 3. So 16 times 3 is 48. And the square root of 16 is 4. Square root of 3. And you can always check your answer. Square root of 48. 4 square roots of 3. As long as you get equivalent decimals, you know you're correct. 72. So reducing the square root of 72, we put in. Go into your table. Go down your y column. Look for a perfect square here in the right-hand side. So square root of 36, if we go down the right column, we find, square root of 72, we find this 36. 36 is the largest perfect square that goes into 72 2 times, becomes 6 square roots of 2. Okay? So again, we bring it down to a perfect square and another digit where that perfect square becomes a 6. The next couple examples here are a little bit different because there's a number out in front. So this 5 is being multiplied by the square root of 90. So what we're going to do is branch out the square root of 90 and just bring the 5 down as something being multiplied. So square root of 90, I don't know if you know this, but 90 ends in a 0, so it's divisible by 9. So if we go down the right-hand column, again, we're looking for a perfect square. So 90, 45, 30, not perfect squares. And fold it off my screen. If I go down to 9 and 10 is a set of perfect squares. So we're going to put in a 9 and a 10. 10 can't be broken down anymore. I know it's not that small, but 10 is not divisible by 1, 4, or 9. So that 9 is the largest perfect square that goes in. So 5 stays out in front. Square root of 9 becomes 3 times the square root of 10. And these two digits multiply together. So we get 15 square roots of 10 as an answer here. I should have left a little bit more room for this. Sorry about that. Okay, so 15 square roots of 10. So again, as a triple check, you could put in what you started with, 5 times the square root of 90, and what we ended with is 15 square roots of 10, and check that they're equivalent. Same process with 3 radical 150. So 3 comes out, we break down the square root of 150. So if we put in 150 divided by x into our table, go down your right-hand column, because again, we want the largest number, and we'll see 25 is the only perfect square here that evenly divides into 150. 4 does go in, but it goes in 37.5 times. We want whole numbers here. So we have 25 goes in 6 times. 3 times 5 times the square root of 6 will become 15 square roots of 6. Square root of 405. Now I'm not sure of my factors of 405, so going into y equals, into a graphing calculator, which is on your Chromebook, 405 divided by x, go down the column, I'm seeing 81 here. And again, I'm very familiar with my perfect squares, so I know 81 is 9 times 9. So we're going to break 81 down. Goes in 5 times. 9 square roots of 5 is going to be our final answer there. Square root of 81 is 9. Exercise 3. Find the length of the hypotenuse in simplest radical form. So 2, 6, and c squared. So our hypotenuse is c. 2 squared plus 6 squared equals c squared. 4 added to 36 is c squared. 40 equals c squared. And we take the square root of each side. So taking the square root of 40 to simplify is 4 and 10. 2 square roots of 10 is going to be your final answer there. Exercise 4. The first one is pretty straightforward. 7x and 18, where 18 is your hypotenuse. So remember, that has to go alone. 7 squared plus x squared equals 18 squared. A couple of us are still making some mistakes here when you're doing radicals. Make sure you square them first. So 49 plus x squared equals 18 squared, 324. We're going to subtract 49 across. X squared equals 275, square root of each side. Now I'm not familiar with my factors of 275, so I'm going to put in 275 divided by x. Brings up your factor pairs. Move it down the right column. I'm not seeing many here, but I will know 25 does go in, okay? Because it ends in a 2575. So 25 goes in 11 times. So we're going to have the square root of 25 and the square root of 11. And we know the square root of 25 is 5 times the square root of 11. Would be our simplest radical answer there. And if we needed to check that, the square root of 245, square root of 275, and 5 radical 11 to give us the same decimal equivalent. So again, if you're not sure if you did it correctly, or if you think you have it backwards, you can put in both answers and verify that they're equivalent. Letter B is a little bit different, okay? Letter B has some extra radicals with it. So I'm actually going to change colors to do this one. Here's our A, our B, and the hypotenuse is 5 square roots of 13. So getting a little bit more into the algebra here, 5 radical 7 squared plus x squared equals 5 radical 13 squared. Remember, when we're squaring things, that means it's the radical times itself. We're going to do a little bit more with multiplying radicals on 701A. But these two radicals squared becomes 5 times 5. We multiply the numbers out in front. It's 25. And the square root of 7 times the square root of 7 is the square root of 49. which is 7. Okay? So what happens when you multiply a radical by itself, you get that radical alone. So again, if I verify it's the square root of 7, I stopped my radical, times the square root of 7, I just get out the answer of 7. Because when you multiply the 7s under your radical, okay, so remember, we're taking a number and branching it into two numbers that multiply to make it, right? It's factors. So we're reversing that process. We're multiplying the 7 and the 7 to get the square root of 49. It does become itself. So 5 radical 7 times 5 radical 7, which is expanded form from 5 radical 7 squared, is really 25 times 7 is 175. Plus the x squared equals 5 radical 13 squared. Now, quick calculator version to find the equivalent to this side here, to use those parentheses. So as I subbed into the Pythagorean theorem, notice I put 5 squared to 7 and 5 squared to 13 in those parentheses as I went. So 5 square root of 13 squared, it's going to be 25 times 13, is 325. So again, I put the 5 radical 13 inside the parentheses and squared it. So here we equal 325. To get an x squared alone, 325 minus 175 gives us 150. Ran out of space over here. Did a little bit too much algebra there. Square to both sides. To reduce our radical, 25 goes into 150 again 6 times. We saw that up top. And we get 5 square roots of 6 as a final answer here. So this side here is 5 times radical 6. 5 squared to 13 plus 5 squared, 5 squared to 6 squared plus 5 squared to 7 squared will equal 5 squared to 13 squared. We're going to find some patterns with these right triangles, some special case scenarios that we're going to look at next time. Exercise 5. We have a square, looks like here. Okay, find the length of the diagonal AC in simplest radical form of square ABCD, given each side has a measure of 8. So looking at our square ABCD, we're going to be finding the length of the diagonal AC, given each side is 8. Okay. So knowing all 4 sides are 8, we have that right triangle formed. So here we have 8 squared and 8 squared to equal x squared. 64 plus 64 is x squared. Well, didn't we just add the same square root 2 times? It's going to give us 128 equals x squared. Well, when I take the square root of each side, wouldn't that branch to 64 2 times? So this hypotenuse is going to be 8 times the square root of 2. That's a pattern that forms with all of these right triangles. And this is really an isosceles right triangle, where these two angles would be 45 degrees here and 45 degrees here. So next class, we're going to see a little bit more of a pattern there. If this side is 8 and this side is 8, the hypotenuse is 8 square roots of 2. Moving on to exercise 6, 7, and 8. Here we're going to do a little addition and subtraction of radicals, okay? And I'm just going to do a little throwback here. Remember, if you have 2x plus 5x, we get 7x. Okay? And if I had 3y plus 4x, could I combine those? I can't. It's just going to say 3y plus 4x because those are unlike terms. So you can combine like terms by adding the digits out in front. We cannot combine unlike terms, right? And that's what this little box here is saying. Addition and subtraction of square roots. If a and b are two positive real numbers, so maybe the square root of 2 and the square root of 3. that sum is not equal to the square root of 2 plus 3. You can't add unlike things. Okay? I can't add the square root of 2 and the square root of 3. That obviously gives me the digit 3.14626, which is not pi. They're very close to pi, though. It's not the same as the square root of 2 add 3, is what this little notation is saying. Those two digits are different answers. You can't add under radicals. So we cannot add unlike radicals. So looking at these couple examples, 2 square roots of 3 plus 5 square roots of 3 is talking very similar to 2x plus a 5x. We take this coefficient. So again, the number out in front is called the coefficient. We add those together. So 2 square roots of 3 plus 5 square roots of 3 is going to be 7 square roots of 3 total. 9 square roots of 2, subtract 4 square roots of 2. So if you start with 9 radical 2's and you subtract 4 radical 2's, you're left with 5 radical 2's. So you keep the radical, just like we kept the x up here when we're combining like terms. 3 square roots of 10 minus 7 square roots of 10 is going to be negative 4, because 3 minus 7 is negative 4 square roots of 10. So we can add common radicals. Well, number 7, the directions tell us exactly what to be doing here. Combine the following square roots by first simplifying the radicals. So this square root of 50, we can't add it or subtract it to the square root of 8 because those are different digits. So what we're going to do first is we're going to simplify each of these. So square root of 50, square root of 25 times 2 is 5 radical 2's. Square root of 8 is square root of 4 times square root of 2. So again, those first numbers here out in front always have to be your radicals. I'm going to subtract in the middle, right? Is 2 square roots of 2. So 5 square roots of 2 minus 2 square roots of 2 gives you 3 square roots of 2. Now to check in the calculator, okay, you can check these every time. I put in the square root of 50 and subtract the square root of 8. If they asked me for a decimal, you would just put it in your calculator. But this tells you to add and subtract by simplifying the radicals. So 3 square roots of 2 is going to be the same equivalent answer. So again, we're rewriting these in a simpler format and adding and subtracting those like radicals together. We're introducing this to you this year. We're going to be doing a lot more work with it coming up in Algebra 2 next year. Okay. Square root of 12 and square root of 3. Those two digits are unlike. So what we're going to have to do here at the beginning is reduce your square root of 12. Now this almost gives me a hint. I need to make a radical 3. I know I can't reduce that anymore. So square root of 12 becomes 2 square roots of 3. Add this square root of 3. We're going to drop it down. We get 3 square roots of 3 altogether. Because there's really a 1 hidden here. So 1 and 2 adds to 3 square roots of 3. 20. Square root of 20 minus 5 radical 5. We want to get radical 5's. That's almost a clue on how to break down your 20. Well, 4 times 5 is square root of 20. Becomes 2 square roots of 5. Subtract 5 square roots of 5, and we'll get negative 3 square roots of 5. Oh, sorry, that fell off the screen. D, E, and F, a little bit more complex because of the digits out in front. So 2 radical 27's minus 5 radical 12's. We can't add and subtract those radicals together, so we have to first simplify. So 2 times the square root of 9 times the square root of 3. So again, pulling out the perfect square in 3, that becomes a 3. And 2 times 3 is 6 square roots of 3. Minus 5, and 12 breaks down to 4 and 3 is 2. So 5 times 2 gives me 10 square roots of 3. So again, I simplified 27 to 9 and 3. Square root of 9 becomes 3, and I multiplied the numbers out in front. So 6 square roots of 3 minus 10 square roots of 3 is negative 4 radical 3. 5 radical 45 plus 2 radical 20. Again, we have to reduce each of these. So 5, 45, I'm going to break down to 9 and 5. Okay. Again, I know my perfect squares. I'm kind of trying to scooch this along. But if you needed to put in 45 divided by x as you're going along to decide what perfect squares divide evenly into your numbers, 9 and 5. We get a 3 here. 5 times 3 gives us 15 radical 5s. And we're going to add 2 drops down. Square root of 20. Remember, we break to 4 and 5. We don't want 2 because we need these perfect squares here. So 2 times 2 is 4 radical 5s. So 15 square root of 5 plus 4 radical 5 is 19 radical 5s. I'm going to pause, try letter F on your own, and then come back in. 4 times 4, remember, is 16. Final answer is 2 square root of 2. And last but not least, to check, if I put in the original equation, 4 square roots of 32, stop your radical, minus 2 square roots of 98, stop the radical, hit enter. 2.28, is that equivalent to 2 times the square root of 2? It is. So again, this big complicated thing is brought down to one single term, 2 radical 2. Exercise 8 is multiple choice. Which of the following is equivalent to square root of 12 minus the square root of 48? I'm going to just calculate this myself. I'm not going to go to my calculator and try to find out my decimals. Typing in those radicals can be a nightmare. Okay. So here we get 2 square roots of 3, 48. Now I'm going to divide 48 by 3. I see a radical 3 here. I want to get another radical 3 over there. Okay. So 48 divided by 3 does give me the number 16, which is a perfect square. So I'm going to have 2 square roots of 3 is what square root of 12 reduces to. And we subtract 4 square roots of 3. My final answer is going to be choice 1. Is 2 minus 4 is negative 2. So that's where you got to be careful with your orders here. Because a 2 minus 4 more is negative 2 square roots of 3. How does this relate to geometry? Exercise 9. So geometric idea here is to find the perimeter of triangle ABC in simplest radical form. So remember, perimeter is the sum of your sides. So we're going to take the square root of 12 plus 2 square root of 2 plus the square root of 32, add them together. So again, the answer is asked for in simplest radical form, not decimals. So square root of 12, we know is 4 and 3, becomes 2 square roots of 3. Square root of 2 square root of 2, I can't reduce that anymore. I'm just going to add 2 square root of 2. Square root of 32, we know does reduce. 16 evenly divides into 32, 16 being a perfect square, becomes 4 square roots of 2. Now be careful as you're adding these common terms. Square root of 3, square root of 2, and square root of 2 are a little bit different. Okay? The only two that can combine together are the last two. So these are considered unlike terms. You can't add 2 radical 3s and 2 radical 2s. Those don't mesh well. Okay? Kind of how we started today. So the 2 square roots of 3 is just going to drop down, plus, well, radical 2s and radical 2s are the same. So 2 radical 2 plus 4 more is 6 square roots of 2. So that's going to be your perimeter in simplest form, meaning we can't combine these radicals any further. They're unlike terms. That's it for our notes today. Your classwork, adding and subtracting a couple radicals, okay, just like we just finished. A multiple choice question, a perimeter problem, very similar to how I just ended. On the back, there is some Pythagorean theorem practice. So again, the front page kind of correlates to this page here, so that if you fan open your packet, exercise 6 and 7 and 8 and 9 kind of follow along side by side there. This back page, I would go back over to the front. We're looking at the Pythagorean theorem, a squared, b squared, c squared, with some of the radicals. Number 9 is similar right triangles. You might need some help or path with that. We'll throw back to Unit 6. Number 11 is Pythagorean theorem looking at a square. Try what you can there. And number 12 is really a throwback to the very first question we did in our notes today. Given the measures 6, 8, and 8 radical 5 in the triangle below, can it be classified as a right triangle? And I'd like you to explain your answer. So does the a squared plus the b squared equal out to your c squared? Good luck. Please email me with any questions. Again, this classwork 7.00 is due for today.